Hello guys, welcome back to my channel. So today we're going to do the question of the day, which is maximum number of k-divisible components, right? So in the question we have been given a tree which requires us to split into max number of components given that the splitted components. So this is the first half. So if you see this example, this tree has been split into two of the components provided that both of these components have the sum of their nodes equals to something which is divisible by k, right? Yeah, confusing. So let's take this sum. So if you see, this is the tree and this is getting divided into this half and this half. Let's say components. So this component has its node 240, right? So each of the components will have its value address value array, right? So if you see, we have 2 as our node. So what is the value of 2 in the values? So 0 1 2 1, right? So this is 1, 4 is 4. So 1 plus 4 is what, 5, and then we have 0. 0 is giving us 1 as well. So this is giving us something 6 and the k. So 6 is getting divisible by k, which is 6 over here. So this is divisible, and the second half, which is 1 and 3, which is what? So 1 is 8 and 3, the third node's value is 4. So this gives us 12, which is again divisible by k. So like this, we need to divide a particular tree into components where the sum of its node in the particular component is divisible by k, which is an integer. The input is given us in n, which is the number of nodes. We have been given edges for, so say there are two nodes, so this will be giving us an edge connecting the two nodes. We have values for each of the nodes, and then we have our integer k, right? So we need to return the number. So here we have 2, so we need to return the maximum number of splits that we can have and get our components, right? So we need to return that. Now, like, our brute force approach could be that we need to traverse for each of the nodes. We'll see for this node whether we have for each of the nodes, for each of the remaining nodes, whether the sum is coming as something which is divisible by k. So if we do like that, let's say for one, we will be traversing for each of the nodes and we'll be checking whether the sum is divisible by k or not. So if we do that, we'll be having our brute force as our time complexity will be something of n to the power of 2, which is n square. And if you see the constraints, we have 3 into 10 to the power 4, and if we square this, we'll be having something which is greater than 10 to the power of 8. So that will give us a time limit exceeded. So we need to come up with something optimal. So what could be our route other than route? What could be an optimal approach? So we see, if we approach something like, for the current node, we have this, right? So if we traverse that in such a way where each of the components give us a sum, whether it's getting divisible or not, and for that returned sum of the child node, we can see for the current node whether it is divisible by k. So if you see this tree, right, and this tree, if it traverse using a DSS, so what does DSS do? It will traverse for the left subtree first, then the right subtree. So if we traverse the left portion, it will traverse the left most child first. So this child has its sum as what? 4. It has 4 as its index, and what is the value of 4? We see that the value of 4 is 4. So we see that this child has a sum of 4, and we see that this isn't divisible by k, so we can't split it, right? So this returns the sum, which is 4. So for this particular node, we have the second index, right? The second index has a value of 1. So again, we'll sum it up. Okay, so this has 1, and we got 4 from this left child, so this will have us 5. So we can see that yes, 5 it is, but it isn't divisible by k, which is 6. So again, we'll call the right child, right? So this right child has 0 as it, and so 0 as its node, and it has a value of 1, right? So again, it isn't divisible by k. So what we'll do, we'll again pass 6. So we'll again pass its value, which is 1. So over here the sum comes up, earlier it was 5 if you remember, and then we are getting 1 from this right child. So it will sum it up, 5 plus 1 6, and we have something which is divisible, right? So 6 is getting divisible by 6, right? So we can make a split over here. So this could be our approach. If you can see, similar to this 6. So right now, if this sum, right, it has a sum which is divisible by 6, so what should it return? It should return 6. We can say that yes, it can return 6. But let's let's use remainder theorem over here, right? So what does remainder theorem say? If two of our numbers which is divisible by a certain number k, okay, so the sum, if two numbers are getting divisible by a number k, then their sum, which is k1 and k2, which is number 1 and number 2, that will also get divided by k. So let's check with using an example. So if we have, let's say 12, and we have something 18, right? We have 18. So these two numbers will sum up giving us what, 30. And let's say we have k as 6, right? So we see that this is getting divided. 12 is getting divisible, 18 is getting divisible. So 30 will also get divisible, right? But what if we turn this to 4? We see that 12 is divisible, 18 is not divisible, so 30 will also be not divisible. So instead of passing 18, what if we pass the remainder, right? What if we pass the remainder? If we pass something, 2 will be remainder. If we do 18 mod 4, what will be the remainder? Remainder will be 2, right? And what will be the remainder for 12? It will be 0. So again, it is not getting divisible. It is 2, will get sum as 2, which is not divide, which is not divisible by 4, right? So we can use remainder theorem, right? So this will help us evade the int overflow. So we can also use the integer value, the 32-bit integer, in order to store the sum. Because if you see, we have the values of each of the nodes could be ranging in the integer level, which could be possibly go up to 10 to the power 9. So if we use this remainder theorem, we can escape that overflow, right? So this will return 0. So 1 has what? Its current sum is what, 8, right? So this, from its left child, what did it get? 0 it got. So the current sum remains 8, and then it will again call the right child. So right child will give us 4. So the right child will give us 4, and it isn't divisible by 6, so it will give us 4. So the current sum for this one node becomes 8 plus 4, which is 12, right? So this will give us 0, right? Because it is getting divided, but we don't have any parent node. So here is where the DFS ends. And yeah, we got our count. Firstly we divided over here, then we again got something which is divisible by k, so we got our count again increased to 2. So yeah, we'll get our answer if we see, right? So I'm sure you got this, right? If not, let's code this up and it will be much more clear to you. So we have our inputs given in edges, and we have for each of the nodes its values. So let's define something like an agency matrix, REs, right? So yeah, vector of vectors, and we have our agency matrix, which will be of length n, right? Now what did we decide? Again, one thing to notice, for each of the component, right, for each of the node rather, we'll be traversing its neighbors, right? So we'll be storing that in adjacency matrix. But again, for each, for this node, if we say what is its neighbor, it doesn't have a neighbor other than 2. But if we call this, right, then it will be an infinite loop. Because if we call, because we got 4, how we got it using 2, because 2 called 4. Now again, if we take 2 as an account as its neighbor, it will call 2, but then again 2 will call 4. So this will be an infinite loop. So we'll traverse for the nodes, for the neighboring nodes other than its parent, because 2 is a parent of 4, right? So we won't be calling 2. Okay. Now let's show this. Yeah, we have been given edges, so we'll take the edges. And so for each of the edge, so let's say 1 and 2 are edges, so 1 will have 2 as its neighbor, and 2 will have 1 as its neighbor, right? If you see, so we'll be pushing 1 which 0 which is the first neighbor will have its neighbor as of 1. Yeah, so we have this one. So if we have something like 0 2, so this 2 node, so this 0th node will have 2 as its neighbor, and again if we see this 2 will have 0 as its neighbor. So we are doing this, right? If we have 0 and 2 as our edge, okay, so we have our agency matrix created. So let's define our DFS definition. In order to call that, we'll have it much more clear. So it returns, we see that each of the nodes is returning its sum, right? So we'll have sum thing returned, right? So we'll have int as a returning sum. So what do we need for a DFS traversal? We surely need our urgency matrix. So let's take that. Got our urgency matrix. What do we need else? We need our values for each of the nodes to map its values. So let's take that. We got our values. Now what? We need our k. We need the current count, right? Then we need the current node, because for the node we need the current node, and we need its parent, right? Because we don't need to call its parent, so we need that. Now we'll define current sum, which will be the node's value firstly, right? So let's define sum is equals to current node's value, right? So we have this. Now we'll be traversing for the current node to its neighbor, right? So let's do that. For each of the neighbor will be traversing current neighbors nodes, right? Now we're going to call the DFS for each of the neighbors, right, other than its parent. So if neighbor is not equals to the parent, which is current, rather parent, right? If it isn't equal to the parent, then only we'll call this. So we'll call the neighbor. So we'll pass the required values for a call k found. So the current will become neighbor and the parent will become the current node. This will help us give us the sum which will add to the current sum, and after this we'll be having the sum for the current node and its child and its left child rather, okay, right? So left and right child. So we'll check if the sum is divisible by k or not. If it is divisible by k, right, then we'll increment the count. We'll surely increment the count, and we should return 0, right? But we can evade that, because ultimately if it isn't divisible, we'll be returning some mod k as it is, right? As we discussed right over here, if you see, we are just taking the remainders, not the original values. The original values were something like this, right? We are only taking the remainders into account, because we don't need to see whether we don't need to generate the sum, but we need to check whether the sum is divisible, right? So for that, neighbors will do, remainders will do, right? So we are just taking the remainders into account, right? So let's call that into our main function. Hmm, let's initialize our count variable, which will be 0 at first. Let's call it by reference, because we'll be needing this count, right? DFS will be passing our urgency matrix at first, then we'll be passing our values, then we'll be passing K, then what did we take? We took count, current and parent. Count will be 0 at first, which will be C. Then we have the current node. So the starting node will be 0 and the parent for the starting node is -1. So we pass that. And yeah, I think we should return after the C. So this will do the job, right? Because we're passing C and we're passing it by reference. So eventually after the DFS has completed, we'll be having the total number of counts, right? So let's run this. Okay, right. So we're traversing this, so it will give us a pair or rather a vector with two indexes. So be careful to traverse this using auto. You can even use vector over here, right? So sample test cases got passed. Let's run it for the hidden ones. Yeah, got traversed. So I'm sure you got this. And the time complexity for the particular question comes up to the traversal because we're traversing for each of the nodes. So it will come as O of n for the time complexity. What about space? So we're using a recursive stack space for each for the DFS traversal. So that will be big of n. And we are generating a agency matrix. So that will be again big of n square for the space. But yeah, you can take that because we have space, right? Time complexity will be big of n and the space complexity will be big of n because we are generating the uh, agency matrix, so we can evade that. But yeah, the space will be n of something like this. Yeah, so I'm sure you got this. Thank you.